So, hello everyone. As Mirko just said, let's continue the discussion on software quality in ROS. I'm coming from Portugal, from INESC, which is also a member of the ROS-Industrial family. I think it's important to note that that every member is contributing in a lot of different ways, and I'll be presenting what I've been doing so far in my PhD. So I think I don't need to give you any further motivation on what robots are capable of nowadays and how they are becoming not only more capable and flexible, but also more complex, and a lot of these complexity, but also the capabilities come from the software and ROS, along with a lot of other libraries and components. And as robots become safety-critical systems, it's more of an issue, and it becomes more and more important to ensure that the software has some quality guarantees to some extent. By doing various kinds of software analysis, we are able to find defects earlier in the development process and possibly reduce risks, as well as maximize the potential savings. So there are a lot of excellent static analysis tools already out there. And I know that some of you have at least tried some of these names. Just to be clear, and to make sure that everyone follows along, static analysis is basically analyzing the source code without executing it. So these tools work all for C++. And they will find various kinds of defects with unused variables, buffer overflows, pointer dereferencing, and so on. But the issue is that while this is all very good, none of this is ROS specific, and there are a lot of ROS specific ways to still mess up the system, basically. I'm sure everyone at some point has forgotten a topic remapping or something along those lines. And one of the first things we learn when getting introduced to ROS is this concept of the computation graph, which is the network of nodes and resources in the system. And we also learn that it's a lot more intuitive to express properties and requirements in terms of this computation graph rather than the lower level source code constructs, right? So it's a lot more intuitive to say, for instance, the sensors should be publishing at a specific rate, or I'm expecting values within a specific range, or whenever the robot bumps into something, the controller should issue a stop command, and so on and so forth. Rather than saying, oh, this specific function in this specific function in this specific file has these preconditions and these postconditions and respects these invariants, right? Usually nobody gets to that low-level specification, which involves also some knowledge of first-order logic and so on. And people typically want to avoid that unless you are really going into airplanes or trains or something like that. So the question is, how can we check these kind of more intuitive and natural properties on the system? And this is something that we've been trying to address in the past few years. And I know that some of you have already heard of or are even using this tool that I've been developing as part of my PhD called ROS. And what's new in ROS since my previous presentations, which were mostly based on these general coding styles and coding metrics stuff, is that ROS is now capable of reverse engineering the computation graph from the source code to some extent, of course, within some limitations, but for relatively common cases, it should be able to read the source code without executing it, and get back the network of nodes and topics they are publishing and services and so on. It even provides a visualization of the extracted graph so that you can make sure that everything is going according to what you expect. But of course, this had a previous step of defining a meta model of everything that goes into a ROS application, right? We had to really think about all the things that go into the system, ranging from the source code entities, like repositories, packages, source files in blue, and then going to the red part of the graph and going into nodes, topics, services, and so on. So we have to include all of this, and the extraction process has to be able to comprehend all of this as well. Then we have to implement the parsers of the source code that actually will map these entities into the entities of our model. So we begin with the launch file, because we define a ROS application as basically a collection of launch files. And we need to parse them to know which nodes go into the application that you are trying to analyze. Then after we know which nodes go into the application, we go into the C++ parser to find the actual topics and services that go into each of those nodes. And one of the benefits of this analysis is that we retain all conditional and unknown values that the tools are unable to resolve automatically. And they are even shown in a different way in the visualization, so that you can later on provide extraction hints to basically refine the model and fix these small gaps. And when you run the tool again, it will take these hints into consideration and basically fix these values whenever needed. So, but those are implementation details. So with that out of the way, we now have a computation graph from the source code, and this already enables some ROS-specific analysis, mostly at the architecture-related properties. And I'll be presenting basically our first two approaches on this ROS-specific analysis, which are based on a query engine and a test generator. So regarding the query engine, the idea is that it allows you to define simple rules that over the structure of the graph. So it basically enables static analysis of this graph. And to give you some examples, let's say that you want at most one publisher per topic in your system. You will write this single line query saying, find me all topics with more than one publisher, and report them as an issue, or give me a warning whenever this happens. The same can be said for parameters, for instance. Let's say that you want read-only parameters that cannot be changed in runtime. You'll write this one-liner again, saying, find me all parameters with any write operations, and report them as well. But you can also get a little bit more complex in the queries that you write, and implement things that are now only runtime checks, like type checking for topics, making sure that publishers and subscribers are exchanging the same type of message. This is something that in runtime you get a warning about, and then it basically starts discarding messages more or less silently, and everything goes wrong. You have to shut down the system, fix the issue, and restart. And with this, you basically get the warning at compile time, and you can fix the issue right away. But not all properties can be checked statically. Some become very, very complex really fast. And this is why we have to also consider some kind of dynamic analysis or even testing in this case. So, for instance, let's say that we have a controller node that subscribes to bumpers and wheel drops and publishes velocity commands in response, right? You might want to say something like, if a stop message is published by this node, then it means that a bumper has been pressed before. right? Looking at the graph, we might guess this might be false because the node is also subscribing to wheel drops, right? And wheel drops probably also trigger a stop. But just to follow along with the example, let's try to verify this property. And in most cases, from what I've noticed so far, people will just write a bunch of test cases manually, probably coming up with a small script that sends a bumper message manually crafted to this node, and then subscribes to the velocity commands and checks that whatever value comes back is within the expected values. But testing these kind of general properties on the interface of a component is basically what property-based testing is all about, right? This is the basic idea. Property-based testing is about specifying general properties, and then the library takes charge of generating a lot of seemingly random inputs that try to break your property and give you a counterexample back. So we can do the same for ROS by injecting this PBT node into the system. The major problem, however, is that topics are asynchronous, and thus we have not always have a guarantee that the message will ever come back. So we have to somehow get timeouts also in the specification. So we tried this, and we noticed that the setup for this kind of node is always the same. So we advertise a number of topics that you are interested in, you subscribe a number of topics you are interested in, and publish a sequence of random messages and check the properties on the outputs. So what changes from one case to another is basically the computation graph that you are testing, and of course the specific properties about this graph. So I don't know about you, but when I did this, it immediately screamed like implement a generator for this. So that's basically what I did, and I've integrated this in Inheres. It's still receiving some last-minute improvements, but I'm hoping to officially release it soon. And the idea is that we now have a single workflow of starting with the source code, extracting the model out of it, and then generating a test script that is suited for this configuration. But by default, the test script only tests for crashes because we haven't got the properties into any point of this workflow yet. And there's this section within the generated script, which is called the internal state, and this is where the user typically comes in. This section contains callbacks for every published and subscribed topic. So, and you implement basically whatever assertions you want within it. So getting back to the previous example, for instance, on line 6, you might want to add a variable for the state of the bumper. And whenever the PBT node publishes a bumper event, you update this variable accordingly. And finally, on line 12, when you receive the velocity commands back, you check if it is a stop, then you assert that the bumper was pressed before, right? And of course, the library quickly finds the counterexample and gives you back the trace that generated it, so, which in this case is just publishing a wheel drop and spinning. It immediately violates the property, so the counterexample is found. But this still requires some programming, so what I'm also working on right now, and I'm expecting to release maybe in the next month, is a small property specification language, which should be able to address a couple of things, namely constraints over message fields, like enumerations and ranges, which is something the default message specification language in ROS does not allow. So you might want to say something like the node publishes on the command val topic, where the message, the linear velocity of these messages is always within minus 0.5 and 1.5 meters per second. Or you might want to say something about the publication rates and timeouts, something like the node publishes on this topic at 10 Hertz, but also include reactive behaviors. So this sort of property like the one we've been seeing so far, something like receiving a bumper event where the state is pressed, eventually leads to the publication of a message within 0.1 seconds where the linear velocity is 0. So it's a stop reacting to a pressed bumper. Of course, right now I'm working on code generators for this language for property-based tests, but who knows, tomorrow we might use the same neutral language to generate runtime monitors, node templates, or documentation, or whatever else you might come up with. It's just use your creativity, and if you do, let me know so that I can possibly work on it. So just to wrap up, static analysis is a powerful tool, a powerful analysis method, and that can find many defects early on. So if you are not already using it, I advise you to start trying it. But keep in mind that the common analysis tools are not ROS specific. And this is what we are trying to address with ROS by extracting the computation graph from the source code, which in turn enables static analysis with queries or generating property-based tests, as well as other things. But in the near future, what we are trying to do is to apply these analysis methods at industrial robots developed back at INESC. We have already have already the process ongoing, so we should be expecting some results back soon. And of course, I'll also be finishing the property specification language, and still I have to enhance the model extraction capabilities of ROS, as it's still missing a couple of things like actions and the TF3, which are also a common source of bugs and are also important entities in the overall design of the system. So I think that concludes my time, and if you have any questions, I'll be happy to address them.
Questions for Andre?
Thank you. I think it's really interesting what you're doing there. Right now, you're only testing topics. Is there a way to test services as well?
Yeah, services are also implemented right now. Yeah. So I'm just using topics as the example because we did a sort of statistical study early on, which showed that topics take like 85% of all the communication uses in ROS versus services. So I'm using those mostly as the common example, but services are already implemented as well. Yeah.
Other questions?
Can you say anything about ROS-II support?
About the
ROS-II support?
So ROS-II is not officially supported right now, as I started this a couple of years ago, and it's mostly a one-man project, so I have my limitations. But yeah, there have been requests, quite a few in this last year. So it's something that we have on the work plan for the next couple of years, for sure. But I mean, these extraction capabilities probably are not compatible because the library has changed. But most of ROS, besides this, the other plugin based checks should work because it's mostly targeted at general C++ and Python, of course.
I was specifically triggered by the property-based testing part where you specified this parameter or the property language, because the current IDL design for ROS-II actually does support things like ranges and enumerations. So I believe actually, so that might be interesting to take a look at.
Yeah, I know that I've checked that things like enumerations and array lengths are already in the message language, but this is one of the things that ROS-I is still missing, and ROS-I is still widely used. So I think it's good to have it neutrally supported in both releases. So, yeah.
Is it possible to detect cyclic loops or deadlocking of loops within the code by your methods?
Not with the plugins we have right now, but I mean, if you know any analysis tool that is targeted at that kind of analysis, it's in general it's easy to make it as a plugin for this, and then you unify all the issue reports in the same place.
All right, let's thank Andre again.
Okay, thank you.